Hello and welcome to the video accompaniment for Chapter 4, Sections 3 and 4. In the last activity that you just worked on, you worked through Section 3 and did some problems relating to sequences. In this video, we'll see that induction is sort of the perfect proof technique for proving some of the formulas that you came up with in that activity. And then induction really goes hand in hand with recursively defined sequences and just recursion in general. Induction really sits nicely with that. And so let's begin sequences and induction. So we're going to apply induction to those recursively defined sequences. We're going to go a little bit further and understand an even stronger form of induction, the so-called strong induction. This will be useful for sequences which are recursively defined not just with the previous term, but with the previous couple terms or however many terms it takes to define the nth term. For example, the Fibonacci numbers would be like this, since the Fibonacci numbers are right. The nth Fibonacci number is the n minus 1th Fibonacci number added to the n minus 2nd Fibonacci number. So we're going to apply strong induction to those sorts of recursively defined sequences. And lastly, I mentioned Fibonacci numbers are a sequence of this type. And so we're going to apply strong induction to those numbers and hopefully better understand the growth rate of that sequence. We'll prove a result about the growth rate of the Fibonacci numbers. All right, let's begin. So after that last activity on sequences, I think we can jump right in with an example of applying induction to recursively defined sequences. So here I've given you the first term of a sequence. I've given you A1 and then given you a recursive definition for it. So I'd like to point something out, how similar recursively defined sequences are to induction, right? We have sort of a base, right? We have to give an initial term that's kind of like our base, and then we have this recursive relationship. This is sort of like the induction step. So it kind of follows a similar pattern, and we'll see that induction really goes well with this sort of setup. So we're going to conjecture a formula and then prove that it's correct for these ones. So an is 2, an minus 1 plus 1. So let's just go ahead and compute some values for this. So I'll have n on the top row and then an on the bottom row. So let's see, when n is 1, we use our initial condition, a1 is 3. When n is 2, we'll do 2 times a1 plus 1, so that would give us 7. 2 times 3 plus 1. 3, we'll take 7, multiply it by 2, and then add 1 to that, so we'd get 15. For 4, we'd get 15 times 2, that's 30 plus 1, that's 31. Let's go maybe 2 more and see if we see it. For this one, we'd get, what, 62 plus 1, we'd get 63. These numbers seeming familiar, are they close to something you're familiar with? 6, we'd get, what, 126, we'd get 127 for that one. And so if you'd like, you can pause it and conjecture your own formula for this. But in general, it looks like each one of these is 1 less than a power of 2. But of course, 2 to the 4th, for example, if I look at this one, 2 to the 4th would be 16. And 1 less than that is 15. So that actually matches up with that one. And so this tells us that our sequence is shifted a little bit from what we thought it was. So let's go ahead and conjecture a formula. So if I have n there, let's try. So it looks like it's going to be 2 to some power minus 1. And to get 15, so to get the third one, I had to use the next power up. I had to use 4 to do that, right? 15 is 2 to the 4th minus 1. So it looks like there should be 2 to the n plus 1 minus 1. And let's see if that holds for the things we have there. So this is our conjecture. Let's see. If I plug 1 in, well, I don't have to really do that. Well, no, let's do that. If I plug 1 in, 2 to the 2nd, that's 4, minus 1 is 3, checks out there. If I plug 2 in, I get 8 minus 1 is 7. That's working. 2 to the 4th is 16 minus 1. Yeah, so it seems like this formula is working for these numbers. Remember, we don't know if this is really going to work forever until we prove it. So let's go ahead and try and prove. So I'll say here result for the sequence above, an is equal to 2n plus 1 minus 1. And let's try and prove this using induction. So we need a base for n equals 1. A sub 1 is 2, or is 3. We know that it's 3, which is the same thing as 2 to the 1 plus 1 minus 1. So the formula holds, and we have a base. So we have a base for induction. So now, our time for the induction step. Assume that an equals 2 to the n plus 1 minus 1. Want to show that an plus 1 is 2 to the n plus 2 minus 1. Remember, you always get the next one by just plugging in n plus 1 for n in the previous one. So we have now our induction hypothesis that a sub n is 2 to the n plus 1 minus 1. And we want to show this. So let's start with an plus 1. And we'll write it like 2 to the n plus 2 minus 1. So an plus 1 is, so use the recursive definition. We know that it's 2 times the previous term, an, plus 1. By induction, so using our induction hypothesis here, by induction, a sub n is 2 to the n plus 1 minus 1. So this is 2 times 2 to the n plus 1 minus 1 plus 1. So multiplying that out, that's 2 to the n plus 2 minus 2 plus 1, so minus 1. And that's it. That's what we wanted to show. So I'll say down here, by induction, the result holds for all n. And that's our proof. So hopefully you're seeing that induction really plays nicely with these recursively defined sequences. It's really easy to use induction on these things. All right, let's take a look at another recursively defined sequence. All right, so what if our sequence is given by something like this? Remember, the Fibonacci numbers are defined using the previous two terms. That's sort of the case here, only a little bit different of a recursive definition, but it involves the previous two terms. So here our initial conditions are a1 is 2, a2 is 3, and then we know that to get the next terms, an is twice the previous term minus 2 terms ago. So 2an minus 1 minus an minus 2. So let's do what we did before. Let's conjecture and prove a formula for an explicitly. So let's see here. Let's make a table again. N and a sub n. So let's see, if n is 1, we get 2. Here we're just using the initial conditions. If n is 2, we get 3. When n is 3, we follow the recursive definition. So 2 times the previous one minus 2 terms ago. So the previous one is 3, so that's times 2 is 6, minus 2, get 4. For 4, we do the same thing. So I'd get 8 minus 3, I get 5. Cool. For 5, I would get 2 times 5 is 10, minus 4, I'd get 6. Oh, Does it kind of seem like there's a pattern happening? 2 times 6 is 12, minus 5, I get 7. So it looks like this is just a rather complicated way of writing the sequence n plus 1. Looks like in general it's just one more than n. So we'd like to prove that this is really true for all of these, right? It's a weird definition for that. It's kind of strange that it turns out to be like this. So we'd like to be able to prove it and know for sure. But the issue here is that, right, we'd like to be able to apply induction, but the issue is that we need the previous two values, right? We need to be able to assume the formula holds for an minus 1 and an minus 2. But with our usual induction, that's not the statement of induction. We can't do that. We only assume it's true for the previous one. So what do we do in these situations? Well, you should ask yourself, why can't we use the fact that the formula holds? Why can't that be our induction hypothesis, that the formula holds for all values up to the one we're considering, right? All values up to k for some k, and then we'll use that to prove k plus 1. Why not, right? If we're on the ladder, maybe it helps to know that that to get to the next rung of the ladder, we can use the rung we're at. But we also know we've climbed up to the ladder to that point. So we know we have all of those statements up to the point that we're at, that those should all be true. So why not be able to use those? It's really all strong induction is doing. It's making use of it's making the strongest hypothesis that you can for that induction step. And so let's state a much stronger version of induction. So strong induction, so-called strong induction. To me, they're really all just induction, and it's the same induction, but of course the statement's a little bit different, and some people do call this strong induction. So again, we want to prove a statement like for all n in the natural numbers, p of n. Remember that with regular induction, we were able to extend this to sets like s, that were like starting at a different number, like s, -2, -1, -1, 0, 1, 2, right? We could start at any number we want. We can do that as well here. It's just a little bit more difficult to state in that way, but nevertheless, this should hold for all sets that look like this, all integers that are greater than or equal to something. Again, all discrete sets with a least element. That's the idea here, is that we should be able to apply this to those as well. And we can. So again, it's saying that that statement, we can prove that that statement's true if we can show that it holds for the first case, and that if we assume p of 1, p of 2, all the way up to p of k for some k, so we assume that's true, and we're able to prove that p of k plus 1 follows, that works too. We don't, remember with regular induction, we just have p of k. But now we get all of these as well. We get to assume all of those. So we get a stronger assumption. We get to use more, hence strong induction. Right, so what this means is that in the previous one, we wanted to prove that that formula was k plus 1 for all k, or n plus 1 for all n, however you want to phrase it. So we get to assume, right. We get to assume ak, but we also get to assume ak minus 1 when we go for the induction on that. And so that's going to give us the leverage we need to prove that that formula holds. We really need to be able to use all the available information. So let's go ahead and prove the sequence we were looking at. It's the same sequence we defined before. Our claim is that an is n plus 1 for all n. So let's go ahead and prove that. So we still need to establish a base. Strong induction works just like regular induction in that sense. So a sub 1 is equal to 2, which is the same thing as 1 plus 1. And actually, since we have two initial conditions, I'm going to go ahead and show those both hold. That way I can assume that n's greater than or equal to 3 and use this formula. I need n to be greater than or equal to 3 in order to use this recursive. So with strong induction, you need to prove as many bases as you have initial conditions. So it works for A1, but I also need to make sure it works for A2. A2 is 3, which is the same thing as 2 plus 1. So the result holds for n equals 1 and n equals 2. So we have a base for induction. A base for induction. And we can assume n is greater than or equal to 3 since we did 2 bases. And that's crucial, right? We need to assume n is greater than or equal to 3. Otherwise, we can't use the recursive definition. So, all right, what's our induction hypothesis here? So assume for some k greater than or equal to 3. Maybe I'll change this to assume k is greater than or equal to 3 because we're going to use k down here. So assume for some k greater than or equal to 3 that a k is equal to k plus 1, a k minus 1 equals k, and so on down the road. So we get to assume all those things are true. Then I'm not going to do a want to show here. No, I will. Okay. We want to show that a sub k plus 1 is equal to k plus 2. So let's try and do that. Well, a sub k plus 1, let's use our recursive definition, is 2 times the previous term, 2 times a sub k, minus a sub k minus 1. By induction, we know what those are. A sub k and a sub k minus 1. A sub k is k plus 1 and a sub k minus 1 is k. So, right, we get to use both of those with strong induction. So this is twice k plus 1 minus a sub k minus 1 is just k. So that's what? That's 2k plus 2 minus k, which is what? K plus 2. And that's what we wanted to show, right? We wanted to show that that was equal to k plus 2. That is, that the output of the sequence is one more than the input, than the index. And so by induction, by strong induction, the result holds for all n. And there's our proof. So I mentioned that the Fibonacci numbers are a sequence like this, right, where it takes more than just the previous term to define it. And so it'll be nice to look at the Fibonacci numbers with these recursively defined sequences. But before we do that, we'll look at one more example of this. All right, so in the last one, we looked at a sequence that was defined based on the previous 2 terms. Here we're using the previous 3 terms. But remember, strong induction, we get to assume that the formula holds for all of those. So let's do it as we've done before, conjecture and prove a formula for a sub n explicitly. So I'll make a little table again, n and a sub n. So when n is 1, here we're just using the initial values. N is 2, we should get 2 out. When n is 3, we should get 4 out. When n is 4, now we get to start using the recursive definition. So it goes like take a sub n minus 1, so 4 plus 2 plus 2 times 1. So 4 plus 2 is 6, plus 2 is 8. And then we do that again, rinse and repeat. So 8 plus 4, 12, plus 2 times 2, which is 4, so that's 16 total. Let's do one more here. Hopefully you're starting to see the sequence. 6, so we'll do 16 plus 8, that's 24, plus 2 times 4 is 8, so that's 32. Well, these all look like powers of 2. So let me give it away for you. Hopefully you can see that. These are all powers of 2. Of course, 2 to the first, right? If we look at the first thing, 2 to the first is 2, and that doesn't match up with the 1. That goes to that one. And then 2 to the second would be 4, and that would go to that one. So this is shifted a bit. So with n, we need to shift it back by 1. So this is 2 to the n minus 1. And we'll just make sure that works, right? 2 to the first, 2 to the 1 minus 1, that's 2 to the 0, we get 1, which is a sub 1. 2 to the 2 minus 1, that's 2 to the 1, and we get 2. It looks like this formula is going to hold for all these, but let's actually prove it. It's going to work the same as the last example, only we get to assume more now. So again, for a base, for n equals 1, a sub 1 equals 1, which is the same thing as 2 to the 1 minus 1. A sub 2 is 2, which is the same thing as 2 to the 2 minus 1. Notice I'm doing a base case for each of the initial values because those don't follow the recursive definition. And in order to use the recursive definition, I'm going to need to assume n is greater than, actually this should say n is greater than or equal to 4. N is greater than or equal to 4. So a sub 3 then is, we know it's 4, but that's the same thing as 2 to the 3 minus 1, or 2 to the 2. So we have a base for induction. And since we did it for the 3 initial ones, we can assume that k is at least 4. And we can assume k is greater than or equal to 4 so that we can use that recursive definition. All right, next step after doing the base, state the induction hypothesis. So assume, remember our induction hypothesis here is assuming that all of the previous values work. Assume that for some k, that, I'll write it down like this, a sub k equals 2 to the k minus 1, a sub k minus 1, 2 to the k minus 2. Since I know I'm going to need the previous 3, I'm gonna just write those out. I know we have all of them, but I'll only need the previous 3. Right? That should tell you that the strong induction really incorporates the regular induction that we've been using, where we just use the first 1. Here we get to use as many as we want. So a sub k minus 2 is, wow, I wrote that really poorly. I apologize. So a sub k minus 2 then would be 2 to the k minus 3. And what do we want to show? We want to show that a sub k plus 1, what am I hoping to prove here, is 2 to the k plus 1 minus 1 is 2 to the k. I'll say, well, a sub k plus 1 using the recursive definition is a sub k plus a sub k minus 1 plus 2 times a sub k minus 2. And now we get to use our induction hypothesis that the formula holds for those. So this is the same thing as a sub k is 2 to the k minus 1 plus 2 to the k minus 2 plus 2 to the k, plus 2 times 2 to the k minus 3. I almost forgot that extra 2. 2 times 2 to the k minus 3. Wow, and what's our goal again? We want to show that that's just 2 to the k. Ooh. So, okay, I need to start a new line here. So a sub k plus 1 is equal to 2 to the k minus 1 plus 2 to the k minus 2 plus 2 times 2 to the k minus 3. Well, let's just 2 times 2 to the k minus 3. Well, let's just try simplifying that. 2 times 2 to the k minus 3, that's the same as 2 to the k minus 2, right? Add 1 to the power. K minus 1 plus 2 to the k minus 2 plus 2 to the k minus 2 minus, making a lot of errors here, 2 to the k minus 2. But look at this now. It might take you a second to see this, but 2 to the k minus 2 plus 2 to the k minus 2, well, that's the same thing. So it's 2 to the k minus 1 plus, there's 2 of those, right? So I could write this as 2 times 2 to the k minus 2. which is just 2 to the k minus 1. So this is 2 to the k minus 1 plus 2 to the k minus 1. But again, there's 2 of those now, and so this is really 2 to the k. And I've kind of run out of room. If you want, include a last line saying, by induction, the formula will hold for all n. But that's really our proof, since we showed that a sub k plus 1 is equal to 2 to the k, and we used a sub k minus 1, and a sub k minus 2 to do that. Cool. All right, let's take a look at the Fibonacci numbers. So we're going to prove 2 different results in the Fibonacci numbers. Fibonacci numbers are really cool. There's lots of interesting stuff that goes behind them, but here we're just going to focus on using induction to prove some results about them, in particular about their growth rate. So we're going to prove 2 results. This first one is going to be helpful for the second one. We'll use it as what's called a lemma, something that aids another theorem. So here we're claiming that the nth Fibonacci number is no bigger than twice the previous Fibonacci number. So recall the Fibonacci numbers. We have 1, 1, 2, 3, 5, 8, 13, 21, and so on. Remember, these are defined recursively as Fn equals the sum of the previous 2. And we need 2 initial conditions in order for this to work. So this recursive definition works only for n greater than or equal to 3, which means in proving this, we're going to need to prove 2 base cases. So let's go ahead and start trying to prove this. Hopefully you're starting to see that induction is actually rather formulaic. It takes a little bit of practice to get there, but it is kind of formulaic, right? Establish the base, assume the induction hypothesis, state what you want to show, and then prove that thing. So proof, so for n equals 1. Ooh, careful here. For n equals 1, that doesn't make any sense. How could f1 be less than or equal to 2f0? There is no f0. So notice here I'm actually using a form of strong induction for just sets. So here, like my set S, this is for all n greater than or equal to 2, so my set S would be 2, 3. It doesn't start at 1, right? So my smallest element is 2 here, and so that will be my base. For n equals 2, f2 is 1, and f1 is 1. Notice 1 is less than or equal to 2. So the formula holds there. Actually, so I said before I'm going to need 2 base cases, but I don't really, because this starts at n equals 2. So as long as I have this base case done, I can assume as n is greater than or equal to 3 when I want to prove my result. And this induction, or this recursive definition, kicks in when n is greater than or equal to 3. So I really just need one base here. So we have a base for induction. All right, write our induction hypothesis. Assume for some k greater than or equal to 3, right? We can assume k is greater than or equal to 3, that fk is less than or equal to 2 times fk minus 1. What do we want to show? We want to show it holds for the k plus 1. And actually, I am going to need the previous 2 here. So fk is less than or equal to 2 times fk minus 1, but also we could say fk minus 1 is less than or equal to 2 fk minus 2. We can use both of those. And what do we want to show here? Want to show that fk plus 1 is less than or equal to 2 times fk. All right, well, let's write out fk plus 1. Use the recursive sequence, use our induction hypotheses, and hopefully be able to prove this. I'll say, well, f sub k plus 1, the k plus 1th Fibonacci number, is equal to fk plus fk minus 1, so using the using the recursive definition for fk. And now I get to assume, using the induction hypothesis, that these two things are true. So each one of those is less than or equal to twice the previous one. So 2 times fk minus 1 plus 2 times fk minus 2. All right. Well, that 2 times fk minus 1 plus 2 times fk minus 2, I factor a 2 out, so you can see something. That's 2 fk minus 1 plus fk minus 2. Well, fk minus 1 plus fk minus 2, isn't that just fk? It is. That's using the recursive definition again. So that's 2 times fk. So what do we have now? We have fk plus 1 is less than or equal to twice fk. And that's exactly what we wanted to show. All right, here that is stated right there, and we finally showed it. So by induction, the result holds for all n. I'll go ahead and just end the proof here. So like I said, we're going to use this to prove another statement about the Fibonacci. This tells us something about the growth rate, right? That the term we're at is no bigger than twice the previous one. But the next result will make that a little bit more concrete in terms of the growth rate of this thing. It'll give it a sequence to compare. So let's use that previous result to prove a more concrete result. So comparing the growth rate of the Fibonacci numbers to another one. So in this one, we're saying f sub n, the nth Fibonacci number is less than 2 to the n. So saying that it's always less than that sequence. It's always going to be smaller than 2 to the n. And this is true for every positive integer n. Remember the result from the previous one. We showed that for n greater than or equal to 2, f sub n is less than or equal to 2 times f sub n minus 1. So we'll get to use that here. And in fact, this little inequality is only based on the previous one. So we don't even need strong induction for this. We can do this with just regular old induction. Proof. So let's establish a base for n equals 1. F sub 1 is 1, which is less than 2 to the 1, or just 2. So now we'll assume, state the, so we have a base. Now assume fk is less than 2 to the k for some k greater than or equal to 2. We want to show that f sub k plus 1 is less than 2 to the k plus 1. So I'd like to use my previous result here. So let's write f sub k plus 1 out using that. So I'll say, well, f sub k plus 1, we know from the previous one, is less than or equal to 2 times f sub k. And then by our induction hypothesis, f sub k is less than 2 to the k. So that's less than 2 times 2 to the k, which is the same thing as 2 to the k plus 1. So what do we have here? We have f sub k plus 1 is strictly less than. So when you have a string of inequalities, you always take the most strict of them. So if you have a strict inequality, you take that. So f sub k plus 1 is less than 2 to the k plus 1. Cool. That's it. We proved it. That's what we wanted to show. So that one we didn't even need strong induction because we got to use this previous result, which we used strong induction on. Okay, so that's it for induction. Good luck working on the homework if you haven't started that yet. When you're done with that, I mean, congratulations. This is kind of a tough section, the proofs and induction together like this. You're doing good making it through this far. Hopefully you feel like you're learning a lot and sort of getting the hang of induction. And as you practice more, you'll definitely get better at it. All right. See you in the next chapter.